Hi, everyone. Hi, everyone. My name is Marion. I'm a student at UC Berkeley. I'm one of the co-leads of the CAM Learning project. We had a pretty distributed leadership structure. We also had two main groups. So we'll start off with the classification group and then move on to a regression group. But we had a lot in common in terms of shared goals for looking through some of the camera time-lapse images that were collected and just poking around and seeing how we could use ideas from machine learning or ideas from the machine learning tutorials to help us process and understand these images better. So we're excited to share what we've been working on and welcome any feedback that anyone has at any point.
Thanks. So my name is Jukes, and our group will be presenting on the binary classification machine learning subproject. We were interested in classifying snow in the canopy with the images from the time-lapse cameras placed at the vegetated sites. So our main goals were to train two machine learning models for classifying snow on and snow off in the canopy, to quantify the errors associated with prediction using these models, compare the two models, and also to have fun working with others on machine learning and the camera data collected through SnowEx. This project was motivated by some interest in knowing more about the timing and duration of snow in the canopy. So snow in the trees influences remotely sensed data. For example, it can influence the pixel reflectance in optical satellite images like those from MODIS and Landsat, and can also influence radar backscatter signals. Also, canopy interception of snow is part of certain snow models. So having a substantial data set of classified timestamped images can provide some validation for these models. So first, let's talk about the camera data. And here is an interactive map showing the different camera sites that were placed in the vegetated areas on Grand Mesa in 2020. So the number in the site name corresponds to the amount of vegetation. So higher numbers like 8 or 9 indicate lots of vegetation, and then the lower numbers indicate sites in more open areas. And the site that we had access to the images for this week was located on the west side of the Mesa site, W9A. This is an example of one of the images from the site that clearly shows snow on in the canopy. So you can see we get a good view of the lower portion of the canopy in this densely vegetated site. For machine learning algorithms, we need to feed the model information in order to train it. And so this information was generated here through a process called labeling or annotation. So essentially we go through and manually classify or label the images as snow on or snow off in the canopy. And we focused only on snow in these upright trees. So we're not including snow on the ground or the fallen trees as a part of our snow on label. And there were 2 images taken per day from September 2019 through August 2020 at this site. So there are a total of about 656 images that we had to label, which we tackled as a team. And we used this package called Pigeon and imported the annotate function to do this. And you pip install it as pigeon-Jupyter. And we split images amongst all the team members for labeling once we decided on the labeling protocol. So as an example, we first copy the images into a list. And then each team member had a section like this that loops through a different subset of the images. And then you go through and click these buttons indicating snow off, snow on, or skip if it's ambiguous or there's an unusable image for some reason. So this is clearly snow off in the canopy. Another snow off, snow on, and so on and so forth. And so the annotate function keeps track of the labels as you do this clicking. And so that's the general labeling process. And once that's done, you can save the annotations into a data frame and export as a CSV file. We then read in all the team's labels and combined into a single data frame. And out of all of the images for this site, 401 were snow off in the canopy and 249 were snow on, which is an okay balance. We then converted the labels into ones and zeros, where 1 was snow on and 0 was snow off. And then we split these labels into a training data set and a test data set with an 80-20 split. We don't have that code integrated here yet, but it was very similar to what was shown in the machine learning tutorial. So that gives us the training information for our models. Then we had to prepare the raw image data, which is the input data for the models. So we converted the images to NumPy arrays and then downscaled them to decrease the processing time. The original images were pretty large, over 3,000 by 6,000 pixels. And with the 3 RGB color channels, this results in over 62 million raw features that need to be input into the model. And so to make the modeling more efficient this week, we downscaled the images to 200 by 150 pixels, which decreased the number of raw features to 90,000. So then the features were compiled into a large data frame where the columns correspond to those 90,000 raw features. And then the raw data is saved and ready for some machine learning. And now I'll pass it off to Evie to talk about building the machine learning models and talk about our results.
Okay, so after saving our data, we now have usable data we could work with. So the first thing we did was to import the libraries we need and all the functions that we need to run our machine learning model. We also had to create metric dictionary because we had plans to build multiple models. So we want to see what the results of each of these models would be eventually. So the first model we used was a random forest classifier, which basically classifies each input into either class by just making decisions using individual features. So this code snippet here basically uses a k-fold stratified k-fold method to separate to separate our data into train and test splits. So we basically we simply use this command here to normalize our data because we know that each data point ranges from 0 to 255. So we just divided everything by 255 to scale them to be between 0 and 1. And for our random forest classifier, we use 1,000 estimators, which is basically specifying the maximum number of trees that we want in our random forest model. And after we run that, these are the metrics we got for the random Forex classifier. We'll be more concerned about our F1 score because our data does not have a balanced class. So we'll concern ourselves with the F1 score, which is basically weighted average of both the precision and recall. Then the next model we use is something we've already seen from the machine learning tutorial, which is the logistic regression. And again, we still did this stratified k-fold split here so that we ensure that every data is used for both training and testing. Then finally, we also did a CNN, which is similar to what we did yesterday, and we trained our model using a CNN. Eventually, this is what we got for as model as for this is what we got for the metrics of the 3 models we use. And I just want to note here that our CNN model, for our CNN models, we use just 3 epochs, and we got this accuracy. So basically, if we increase the number of epochs, we should get better metrics. And the logistic regression tends to perform better in this case. So, and we got a 96% F1 score, which means that 96% of the time, our model will be able to predict when there's snow on the canopy or off the canopy. So we'll just move to the next group, next team.
So that was the classification group, and then we also had a regression group, which I'll introduce. So the main contributors for the regression group were myself, Danny, Katie, and Ching, and our goals were to train a regression model to extract the snow depth from the time-lapse imagery using supervised learning. So take pictures from the cameras that had the snow poles in them and train the computer to tell us how deep the snow was in each given picture. And then we evaluated our model for accuracy. We tested out some potential improvements and learned some things and have some ideas about where we might go next. But this was a new experience with machine learning for all of us. So we learned a lot from the process. Our biggest motivation for this process was the fact that the SnowEx time-lapse imagery had been previously labeled for snow depth using a pretty time-intensive manual process where people were looking at every single picture and identifying where the poles were and then converting the number of pixels that were covered by snow into depths. So we were hoping that we could come up with a machine learning method that would do a better job of doing this more quickly and also complement another process that Katie and some other people were working on using some identification of the pole itself and pulling out that image. So it's an interesting comparison versus something that's more based on identifying the depth probe versus, or the pole versus just putting either all or part of the image through some machine learning processing. So we're hoping that something like this might help the team looking at the pictures identify how deep the snow is in each picture a little bit more quickly without as much manual processing. So I'll hand it over to Danny to talk through some of the next steps.
Got about 2 minutes remaining.
Got it. I'll basically fly through this as quickly as possible. A lot of it is actually similar stuff that the other group had shared. So the data set that we used was this open vegetation site, W1A. So essentially it's pretty open there, very sparse. We installed some packages here, TensorFlow, along with OpenCV. This is just all of our imports in. And essentially what we did is we saved all these files to one location and stripped all of the date time metadata from the image, in which we used the SQL database with the corresponding measured snow depths for each image. And we basically spliced those two together, so tied them up so that each image with its corresponding metadata was used to, or that date time was used to match to the actual measured snow depth at each of these images. So essentially we then used CV2, which is OpenCV, to shrink down these images to 200 by 200 pixels, and then essentially, yeah, that's just to shrink them down and put them into these NumPy arrays in order to just have the RGB values in in these, NumPy arrays. Next, this is here, sorry, where we pulled the snow depth values from the SQL database. Here's what they look like over time. We basically did the same thing by cropping the images in order to reduce the number of pixels and hopefully make more accurate guesses as to snow depth. This is what a post cropped image looks like. So it's just centered around the pole. And essentially what we wanted to do is compare the two values, compare the two runs on uncropped and cropped images. And I'll just forward down to basically our results. This is all essentially the same process that the ML tutorial went through, and we just applied our data set to it. And essentially what we wanted to look at is a full image linear regression, full image CNN, cropped image linear regression, and cropped image CNN. And our hypothesis was that the cropped image would be more accurate. And essentially that is what we found. We had a lot of issues with the regression analysis for both the cropped and uncropped images. They seem to be kind of divergent, but the neural networks were pretty decent, better than honestly we expected. And essentially the R-squared values for the uncropped were around 72% versus 84% for the cropped images. And our MAPE values are insanely off because of some zeros in our data set, which just throw everything off. But essentially, this is what our predicted values look like versus our true values in the deep neural network for cropped images. And here is kind of what they look like for the uncropped images. Sorry for having to go through this so quickly. But hopefully you can delve through this notebook a little bit more if you want some of the more details. And if you have any questions, please feel free to post those. Thanks.
And then just to finish out, our thoughts for the future include first that we had a relatively low number of pictures that we were working with. So we ended up with around 300 that we were looking at, and we were thinking that having more would be helpful. And then the other thing is we had this dream of doing a combination classification and then regression, because our results tended to be a lot worse for the pictures that had very low or zero snow depth. And so our idea for a next step would be to first classify our pictures as having snow or no snow. A lot of the pictures were from the summer, using some of the methods developed by the other group, and then only run the regression on the images that had snow in them to see if that worked a little bit better. But thanks everyone for listening, and yeah, huge shout out to our entire group. We had a great time and learned a whole lot.